Yeah, can you hear me?
Yep, we can hear you. Hi,
Cool.
Henry.
Hi, how are you? Good?
Good. How are you?
Good, good. I didn't realize that today was San Valentine. It's probably like why it's not so much people are showing up yet.
I see.
Yes, do you want me to? I don't know how I can actually share my screen, or do you want to say something before?
Um,
Or?
yeah, I can just give a quick introduction and then you can take the wheel. So, yeah, I guess we can start. It's exactly 8 p.m. So, hi, everyone. Welcome to this tech talk on LLM application architecture and design patterns with Dr. Henry Ruiz. He's a GDE or a Google recognized developer expert in machine learning. And we'll be covering different design patterns and architecture principles that have sprung up since the inception of these Gen AI technologies in this talk. Uh, just a quick reminder, we will be recording this event and it will be posted to our YouTube channel, GDG Chapel Hill. So the agenda is roughly like this. We'll mostly use the time we have today for the tech talk and then leave a little bit for a Q&A at the end in case people have any questions. And of course, you can always post questions while the talk is in progress, and I'll make sure that it gets answered. A little bit about GDG Chapel Hill. If you're joining us for the first time, we are a chapter based out of Chapel Hill, North Carolina. It started as a bunch of CS students and tech enthusiasts at UNC trying to create a community for exchanging info around the latest and greatest in software development and tech in general. If you're not already a member and are watching this on YouTube, be sure to visit and join this chapter by going to gdg.community.dev/GDG Chapel Hill. A little about me. I'm a software engineer based out of Raleigh, North Carolina. I'm currently also building some Gen AI based features at this company called ShareFile. And yeah, I sometimes do talks at this chapter like this one. Uh, and if you would like to network with people, feel free to drop your LinkedIn in the chat or just uh, describe yourself a little uh, in the chat or by just unmuting. Uh, Here's a little about Henry. Actually, Henry, if you could uh, introduce yourselves to all of us, that'd be awesome.
Yeah, sure. So I am a Google developer expert in machine learning, and also currently working as a research scientist for Texas A&M University, specifically to Texas A&M Aguilar Research. So my research is pretty much around the application of in the intersection between remote sensing, AI, machine learning, and recently I have been focusing on exploring how LLMs can be used as a reasoning engine, specifically to orchestrate analytical pilots, such as is the kind of application that we do in the remote sensing context, which pretty much what we do is we take data collected from different sensor platforms, such as UAV, satellite data. We are exploring how we can use the information that we collect with these sensors, and we can integrate that and put it into the context of these LLMs that these days actually can understand images, and how we can use that to address different scientific questions. So I am right now focused. I am just my expertise right now is in well. So I come from the industry background. I worked in the industry for almost 10 years, but recently I just since I finished my PhD, I have been in the academia, but this is what is my experience about. So today I just gonna be trying to share with you guys some of the recent advances in terms of how LLMs and generative AI models have been using around in different applications. It's gonna be kind of like taking you guys to a journey of show you um, how these sophisticated models these days can be used for things like reasoning engines and like to do function call and all of these kind of things. It's gonna be kind of like an introduction to the state of the art of these models, and so the immense possibilities that you guys have to develop applications using this new generation of AI models. So I will share my LinkedIn. So if you and I don't know, are we ready to start now? And
Pardon? I think I didn't catch the last part, Henry.
so are we ready to start, or so
Oh
can we
yeah,
start now?
let's get rolling with the talk. Let me
So
s-
it's good. Do you have? I don't think that I can share my screen now, but
let
okay.
me see if I can give
Yeah, I
you.
think that now I can do it.
Okay.
Okay, so please let me know if you guys can see my screen. Good.
Yep.
Okay, sounds good. Yeah, can you guys hear me clear? The microphone sounds good.
Yes. Loud and clear.
Okay, okay, sounds good. Well, so the title of the talk today is LLM applications, and I'm gonna focus, as I mentioned, specifically about the components and design patterns that have been evolved around this type of model. And I will first start with an introduction about what we can do with machine learning these days, and so how we can come from these feature engineering based methods, talking specifically about traditional machine learning models, up to what we have today, which is generative AI models. So if we go back and we recall what machine learning is, it's all about you have a data set. A data set can be a structured and unstructured, and you're gonna try to fit that data into an algorithm with the goal of this algorithm to be trained to find the best parameter that fit our data. So at the end, what we have is the trained model. So the model is the combination of the algorithm, which define the set of steps that we apply into your data to find those parameters and, and learn those parameters. And so the set of parameter itself that the algorithm learned during training. So if you have the data, we have the algorithm, then we train the algorithm for using different techniques. For instance, using neural network, we apply optimization, um, algorithms such as gradient descent, but there are different other approaches to train machine learning algorithms. Like traditional machine learning methods used to be based pure in math and statistical principle. These days are more, it's more like a optimization based approaches. But there are different ways that the algorithms learn those parameters. And so this model is what we finally end deploying in different contexts, deploying in clouds, mobile devices, and everywhere. And so this is an iterative process because we refine the parameters of the algorithms until we got into the point that we got the kind of a score that we expected from uh, this model. So this so these days we talk about mainly two types of machine learning. There are others such as reinforcement learning, but today I just gonna blow up these two types of machine learning, which are the more common approaches. Predictive machine learning model consists of we present the algorithms with samples and observations, and we train through a supervised learning approach, which that means that we are providing samples and also the labels for for each m for each point in my data set. So at the end, what the model gonna tend to do is learn the relationship between the data points and the respective labels. And so by following these principles and applying different algorithms, So we have a trained model which can be probabilistic or deterministic, and so the model can be used to predict the value of a discrete or a continuous variable. So this is very important because when we talk about predicting the value of a discrete variable, we are talking about classification. When we talk about predicting the output of a continuous variable, we are talking about regression problems. So it's really important to mention that because based on that we do research in terms of what algorithm fits better into your data set. So this is kind of the formalization of the traditional predictive machine learning models. So we, based on the data, which is going to represent as a matrix X and Y, we try to come with a function that enable us to do predictions, which we're going to call it Y prime. But these days we have the generative AI model, which the principle behind is that we have a huge data set of non-structured data such as images, videos, text, or similar type of data, and we're gonna train an algorithm to learn the underlying parameters of the distribution. So by doing so, the algorithm is gonna be able to generate new samples. So this is something that is not new. Random sampling has been for a while. There is a theorem in statistics that is called Lotus, which says that if you know the parameters of a given distributions, you are able to use those parameters to do random sampling. So in this case or in this scenario, the reason why we need neuronal networks to do so is because we are talking about of millions and millions of parameters, and which are those that this kind of model has. So that means that we can rely on optimizations to learn these parameters, and then we're gonna have a trained model which is able to do sampling, and this sampling means generating images in different modalities. Those modalities could be from text, image, or audio. So what we expected after learning the statistical properties of the training data set is that the model is gonna be able to generate samples that follow the same distribution of the training set. So that means that we don't expect the model to predict labels or classes or generate images of dogs if the model was trained to generate images of a cat. So this is something that we really need to understand. So this is the formalization. We're trying to come with a way to learn the parameters of the P, what we're gonna call P is the distribution of the training set, and doing so we can uh, have a probabilistic model that can generate new data. So, but the most important part here is that we need to understand that this model only handler and process vectors and numbers. So that means that we need to take that data and somehow transform that data into a vector representation. And it's in the vector space where we actually are able to find relationship between those data points, applying different techniques such as neural networks. So the cool thing about this is that once we are able to come with these fixed representations, so we just rely on math to be able to find the relationship between those data points into the space. So what I mean is that if I have a data set of images of a cat, at the end, applying some kind of transformation, we're gonna have a bunch of different data points in the space that it will allow me to know if this picture of a cat is close to this picture of a dog. So this is the kind of thing that we can do. So this numerical representation of by data, which again could be a structured or non-structured, some in form of images or audio or whatever. So it can be handcrafted using fiction engineering, or it can be also learned by the model during training. So we can spend time, which is what we used to do in traditional machine learning algorithms, trying to find with a way to transfer that data into a fixture or into a vector representation. We're gonna call fixture vector, or we can train a model, which is what we do these days with the embeddings vector when we have an encoder. The encoder is gonna learn how it can represent or it can model the information that is in my data set into a low vector representation. And this is the low vector representation that the decoder is going to use further to uh, generate data or reconstruct do the inverse process of reconstructing the data. So this is what we have today. We have multimodal models where we can just pass images, audio files. We have Gemini, for instance, where we can pass different type of data, and the model is able to understand and uh, find patterns in this kind of data representation. So by internally, what's happening is those data points are transformed into a numerical representation, and the way that the model actually do that is through the encoded process. So to the encoding process. But before, again, so we used to rely on feature engineering. These days we use pre-trained models to do so, or embeddings-based models. So this is the workflow. It's pretty straightforward. We have the input data, which is images, video, audio, Excel files. So we pass that data into some kind of transformation function that is gonna transform my data into a vector representation that can be projected into the vector space. So there, the machine learning algorithms is gonna do the magic. They're gonna do the magic trying to find relationship between those data points into the space, and this is gonna happen to the training and the evaluation process. So this is regardless of we are talking about traditional machine learning algorithms, generative AI machine learning algorithms. This is a very standard process of how this algorithm actually learn. So then at the end, what we call embeddings today is a dense, compact, fixed size representation of data. Images, audio, text, this kind of data we call sparse representation of data. But when we apply an embeddings model that is able to come with this low dimension representation, which at the end is what we call embeddings, this then representation is that that the model internally is gonna be using to learn patterns from my data. So we come from this sparse representation of my data to this dense representation of data that we call embeddings. And again, so this is this process is generally done by uh, this should be learned by the model itself, or we can actually do this applying different feature engineering techniques. So this is really important to understand because this is the base of what we call multimodal model these days. So, and all of these advances are going into the direction of one day reach out what we generally call general AI. Like which consists of giving machines the ability of understand the world in the way that how actually human does, and to go to be able to get into that point. So we need to be able to understand data in the way that we humans do. So we are able to kind of extract information from different multimodal representation. We recognize people, but we also can hear what is going on into my surroundings, and I can also see things, and I can make relationship between objects in the world. So the question is how I can actually do this computationally, which is what is actually behind of what we call multimodal models today. And in the way that we do so is that we apply techniques such as contrastive learning that we're gonna see later how this thing actually work. And so what we're gonna tend to do is we're gonna try to come with a joint embedding space. Joint embedding space is we're gonna try to find uh, uh, we can call vector space where I can actually identify relationships where I can compare multimodal representation into the same space. So imagine this a bunch of different images of a cat and videos of cats or these like text related with cat. So how we can actually find this joint embedding space where I can actually find that this picture of a cat somehow have a close relationship with this with a video of a cat, or like or how this picture of a dog have some kind of relationship with this video in the park of a dog playing. So in the way that actually happened is that we use different techniques such as what that's what I mentioned before, contrastive learning, where I try to teach the algorithm to to generate an optimization process to find this vector representation where I can compare this multimodal data. So at the end, our goal is how we can represent multimodal data into the vector space, into a same vector space, what we call joint vector space, so we can find relationship between not only images but audio files, video file, text, and so on. And in the way how this model actually become multimodal, when I say multimodal, is that those models are able to understand text, images, audio, and video is using techniques such as uh, uh, contrastive learning. So this is a really interesting paper that you guys can check out. It's called LIMO-A, learning multiple modalities with one expert mixture of expert model. So this is one of the foundation behind of Gemini. You can go and check it out. This paper. This paper was published in June 9 of 2022, and so it can give you some of the foundation required to understand how these model actually are trained to be able to find this joint embedding space where multimodal data representations in form of vectors can actually be compared. So just to explain briefly how contrastive learning actually works is that so we're gonna have two optimization tags. One which is gonna be focused on in try to minimize the distance between those observations in my data set that have some semantic relationship. Like so that's mean that I want to minimize the distance between this picture of a dog, or showing this example, I want to minimize the distance of this picture of a raccoon and this video of a raccoon, or a similar picture of that animal. But I'm gonna have another optimization task, which is try to maximize the distance between that raccoon and everything else that is not a raccoon or something similar into the feature space. So this is what generally we do for training these models using contrastive learning. So in summary, this approach involves training encoder to minimize the distance between representation of similar data, which we're gonna call positive pairs, and maximize the distance between representation of the similar data, which is gonna call negative pairs. So this has opened to have model like Gemini that is for me the only LLM that is truly able to handle multiple multimodal representations. So in the way that this actually does is an architecture, a transformer-based architecture based on mixture of expert that use techniques such as what I mentioned before, based on contrastive learning to understand the relationship between different multimodalities that have some similar semantic meaning. So the input is going to be multimodal data, which could be images, videos, audio, and any kind of modalities um, that so far this model is able to handle. We're gonna have a router. This router is it's gonna be our neural network that, based on the input, he's gonna be able to understand or to know which expert, which is a set of independent neural network working together. So this router is gonna be able to understand which expert can be processed that input and pass through the rest of the layers into the architecture. So at the end, so this model have evolved from a traditional feature engineering approach where we used to manually try to come with different ways to transform my data into a numerical representation for a vector, which, like in this example, imagine that you have been asking to train a machine learning model to classify um, flowers based on the petal and the sepal dimensions. So traditional machine learning relies on your feature engineering skills. So we used to spend a lot of time trying to come with a way to extract that information so we can create um, this structure representation in form of like this Excel file that you see here, and we can pass that to the model. But then later on in the research, like we come with the sophistication of deep learning models that were able to learn those features by themselves. So what deep learning architectures come up with is that we used to have these sophisticated feature extraction layers. For instance, in computer vision, we used to have convolutional neural network, and so in the kind of some of the building blocks of this kind of architecture are the convolution layers, where they are focused specifically in transform and apply different transformation on my picture, so on the images, so they can actually find uh, feature that they can potentially use later in the architecture, in the inference part. This is the feature extraction part, all the layers that extract feature, and the other the other layers, which are fully connected layers, are focusing in take those features and try to do inference. So this was a breakthrough advance in terms of AI, because now in those scenarios we come with this set of features were complex. So we have these new kind of methods where they were able to extract those features by themselves, apply different feature extraction techniques. But then one of the problems that we have with this model is that for the different multimodalities, computer vision, speech recognition, we need to have a specialized feature extraction layer. So so this is how, then so researchers start thinking about how we can come with a single architecture that can be somehow be adapted for different multimodalities. How I can actually use the same building blocks to train models for computer vision, for speech recognition, for natural language process, and so this is where actually transformers come out. Like transformer architectures is a deep learning architecture that initially was released with the goal to try to improve it, and kind of try to kind of improve and somehow uh, eliminate some of those problems that we used to have with traditional natural language processing architecture, such as like the capacity of being able to have a longest memory, also to uh, be able to have long sequences, you know, longer sequences. Another, how we can actually parallelize the training of these kind of architectures for this kind of tasks, and also they provide a different ways to do parallelization. So Transformer opened the door to a new generation of deep learning architecture. I don't gonna focus so much in the but we don't have so much time, but there is so much things to say about this architecture. So they prove in this paper when they release again trying to kind of attack some of those challenges that we used to have with traditional uh, natural language processing architecture such as LSTM and recurrent neural network and so on. And so they come with these attention mechanisms that what pretty much they allow us or they enable the model to do is that instead to the model need to kind of process all the sequence as a whole. So we're gonna have this attention mechanism that are able to pick and identify in that long sequence which are those elements that are more important, and also what is kind of the relationship that exists between the order in this sequence. And this opens the door also that we can train this model in a more optimal way, so we can actually parallelize the transformer blocks during training, and then so we can actually improve scalability. So at the end, what actually transformers come with is with a method that says anything that we can pretty much tokenize can be fed into a transformer model. And when I say tokenization is a term that is more related, is more closely related with natural language processing, but this has been quickly adapted to other modalities. Today we can tokenize images, tokenize different data. So then this standard architecture that this kind of new architecture that come with this new method that says that anything that you can tokenize and you can represent as a sequence, so it can be fed into transformer, open the doors to the what we have today, which is the multimodal model. So this is where we can pass videos, audio files, text, and they're gonna have their own encoders. The encoder is gonna transform these different multimodalities into a sequence representation, and then they're gonna be projected into the multimodal projection space, and then different attention mechanisms and transformer blocks is gonna be applied there. So we can use that to train model for different things, you know. So then if we get back to the same problem that we initially solved using traditional machine learning models, and then we also saw how can also be solved using deep learning architecture, how we can actually solve the same problem using transformer. Well, in the way that we can do is that we convert that image into a sequence. So the simple way that we can potentially do is that just taking that picture and start patches. It's just imagine dividing the picture in different cells, and each of those cells is gonna be one part of that sequence, and then we can pass that into the transformer blocks. So this is what we have so far. Transformer in summary push forward the field of large language models and generative AI model initially to address again the limitation of traditional NLP architecture, but soon they were kind of start being adapted in other contexts, which are computer vision. And today, Transformer is the backbone architecture for many state-of-the-art models such as Gemini, GPT-4, and this kind of thing. Generative AI is transforming how we interact with the technology today. But so, what is actually wrong? Why these days people is only talking about generative AI? So why people is just trying to solve um, kind of every problem that we used to kind of approach using traditional models, traditional methods? Why people just want to move into the world of generative AI models and LLMs and all of this kind of thing? Well, one of the problems with traditional models, this includes machine learning, feature engineer based algorithms, and also deep learning based traditional ones, is they don't have the capacity of do reasoning. Reasoning is what to us humans gave us the capacity to learn from just capacity of learn from just a few examples. So we can just pretty quickly extract information from the context and do inference and do kind of so let's make an example where we can actually see the limitation of traditional approaches. So imagine you want to solve this problem. So I would like to have a model that can take the the last character of each word in a given sentence, and it can concatenate it. Like imagine Bill Gates, and the decoder is just gonna concatenate out and this. So it's a very kind of simple task that you can actually solve with a one line of code using Python or any programming language. How I can actually use machine learning to solve this problem. So well, so if we try to come from if we try to use traditional machine learning models, but then you probably are thinking that we're gonna need to have a huge data set of samples, so that the model is gonna have to learn from, and then eventually the model is gonna be able to find that relationship. But the problem with that is that so what about if there is a sentence that is not into the it's not considering or is out of the distribution of the training set, So the model is gonna start having a lot of problems. So how we can solve this problem using large language model? Well, large language model is a type of generative AI models. So we already know how these models are trained. We just pass non-structured data into this model. These models trying to learn the parameters of the distribution of the training set, and then they can use that to generate new data. And so, but at the end, what LLMs are, like we can provide with that with like as a providing a high level definition as a LLMs, a type of generative AI architecture that usually means 1 billion of parameters based on transformer that is trained to predict the next token of or sequence of token into a given text, in this case for the text-based model. But in low level, more from a software developer perspective, just to file index, the weights, and the model itself. So at the end, model are just a statistical model of language. So they assign probabilities to every possible word into the vocabulary that is aligned with the prompt that we are giving. That means that we can, from that distribution of tokens with his respective probability, I can identify which of those tokens have the highest probability, and I can, based on that, predict the next word. You can also think of training LLMs as training a patterns to mimic human language. So you're gonna take a huge data of text written, and we're gonna pass that to the model. So the model is gonna try to find um, the semantic relationship between the different words in the vocabulary and how these words can be connected. So usually how these LLMs are actually trained are, so this is the data set that was used to train GPT-3. As you can see, was a lot of data from Wikipedia, different books, information gathered from internet, and so all of that data, all of that information after like going through different pre-processing and kind of filtering techniques. So where that data set was fit into this LLM's architecture, and then this model were trained to predict the next token. So those model basically what they do is we provide with an input. For instance, the sky is, and because the LLMs understand language and understand the semantic meaning of the words and how they can actually be connected to each other, so it can predict this probability distribution that tell me which are the closest word that could potentially, based on the training set, be close to that statement, and then it's gonna tell me that the next token is gonna be the sky is blue. So this sampling process of taking what is the next token. So there are different ways to do so. The simple one is just if the model come with this probability distribution, that means the token and the likelihood of this token to be selected as the next token. So I can just take the token that have the maximal probability, but there are more sophisticated techniques that are less sensible to bias or noise. That means that it's a huge research area in terms of how the next token is actually chosen. So now getting back to the simple problem of how I can actually use machine learning to, like come with the concatenation of the character of each word. So based on what we learned so far from LLMs, it seems like we can potentially use LLMs to solve that. Especially because, like there is a paper that was released in 2020 where they explain that LLMs are just future learner. Future learner means that it's a way to train models in a supervised way that where they can actually um, learn to generate or learn to pattern from a few example of training data. Like a few example of data. So future learning is refers to the problem of learning the underlying pattern to data just from a few training samples. So well, we see that even that the model, the LLMs, is able to generate the next token, you're still saying that the model failed. You can still saying here that the model failed. However, so we found that because these models are future learning, we can actually provide with more context information to those models so they can actually use that information um, to generate the output. And the reason why they can do is because these models are autoregressive model. So that means that they only generate one token at the time. But the interesting part is that they generate one token at the time, but they are able to get back to the previous steps, and they are able to use those previous tokens to use that into the context. So that means that at the end, what we have is a chain of probability that's um, each tokens contribute with the output sequence of token that we have at the end. So that means that if we provide more samples, more data in the context that can tell the model how can actually it can behave, so it's gonna maximize the potential of the model to come with the output that you expect. And this is exactly what we do today. Like is we add in some information such as, okay, imagine that this is the input and this is the kind of output that I expect, and I provide with some few short samples to the model. The model is gonna be able to succeed in that task. Again, this is because the autoregressive nature of these models. The key idea behind of that, this has been studied since 2017, where DeepMind published a paper and on how natural language, how like LLMs can be used for solve problems. Um, so providing that with the intermediate steps that giving the models context to generate the outputs. So the key idea is intermediate steps. There are different techniques today that we have, and this is the foundation of what we call reasoning. But at the end, it doesn't matter what technique we use. If we use RAG or we use, there are different kind of ways to provide these models with the reasoning capabilities and be able to use samples to know exactly how they can generate the output. We're gonna see later how actually that works. But at the end, the most important part is that it doesn't matter what technique that you use, is how you can model, providing with the intermediate steps that give context to the algorithm so he can actually know how to generate the final output. So it has changed the way how we interact with LLMs today. Before we just have a question, we just prompt the model and we got the output back. But today we can further use LLMs to solve problems that require reasoning, require external knowledge, or even do some computation in the background. So about how we can actually address this kind of question, and this is what we're gonna focus in the part where we're gonna start discussing about the different design patterns. So this is to be able to the model not only the standalone question, but be able to do some kind of reasoning, uh, extract information from external knowledge, and even do computation. So we need to augment the language models, and in the way that we do is that we take advantage of the context windows. You know, one of the reason is what I really kind of um, for me, Gemini is a game-changing model. Is that because people don't realize the importance of the context windows. You know, Gemini provide almost no, I think that today provides 2 million tokens, but people don't realize that. You know, people are still comparing Gemini with other models, but they don't understand that there is a huge advantage of having this amount of token extra where you can use that exactly to augment the language models. And the way that you can actually do is that you can enable the model to go and extract information and bring information from the environment. When I say the environment, from an external database, from an API, from everywhere, even from the physical world, we have this into a robotic platform using things such as like uh, function calling. You know, today we have this thing function calling where if we provide into the context the signature of the functions that the model is going to have access to. So even though this model don't actually execute code, they are really smart transforming the text into a structured data, so they can actually provide us with a function that it can be potentially used to solve a specific problem. Another way that this can be used to augment this model is using retrieval techniques such as RAG, you know, retrieval augmented generation. This is something that people are doing these days to avoid the model go pure to the general knowledge and the information that the model memorized during training, and we can actually bring external information using RAG system. So you know, like is imagine you being prepare yourself for a test. Instead to you need to memorize everything, you can just go to your notes and check what information you have there written that you can use in the context to solve a specific problem. You know. So the key component here is the context windows. So these are really important aspect and that need to be considered these days to do this all of kind of benchmark also. You know, right now the leader in the industry of in terms of LLMs is Gemini, and but now let's start thinking about how we can put all of these components together. So this is the anatomy of an LLM app. You can see here the different components that an application that use LLM in the backend can be. It's kind of the building blocks. We're gonna have the user input, which is pretty much the prompt. This prompt could have a structured or unstructured data. It's gonna be passed into a form of chat with the. So generally, what we do is we implement some word rails. The word rails they ensure that the output and the input quality of the input of the output of the uh, output generated by the model have is follow some specific kind of constraints. So, you know, for instance, a lot of people complain about Gemini kind of being very restrictive, but actually, but the reason why they actually do so is because they want to make sure that they don't go against allow people to use this LLM for things that they shouldn't uh, use. That means that when I talk about the WRL, is that you can have a model. Generally, you use machine learning model here, so you want to be those models to be light because it's gonna be in inference time. So that means that they need to be pretty quickly. But you just pass the input to your application, and this gonna pass through these web rail models that they can actually identify if the input have any content that could be like um, pretty much that they don't follow the safety constraint that you have defined for your application. You know. And in the backend, well, we have the different APIs such as LangChain, Llama Index, which provide a high level way to interact with these LLMs. But you can just go also directly and um, use the APIs that providers um, have released, like a Gemini API, an OpenAI API, or You can, if you want to go to a low level, such as, for instance, if you don't find a Python API for Gemini or for OpenAI, but you want to run an application that is running into a Wash or even into a, like any kind of device that you can potentially think that have connection to internet. So you can just use the REST endpoint. So the way that we actually interact with this application is using conversational internet interfaces too, like Gemini Chat, AI Studio, or so on. And at the end, the kind of building blocks that we need is we need to have the way to do function calling, different ways to improve prompts and structure prompts, the structured outputs, and all this is what this kind of libraries provide. And we also have a bunch of components focusing in operations. I think we're not focus so much time, so much about that, but it's in the same way that we have DevOps and we have LLM ops, we also have in the way that we have DevOps, we also have LLM ops, ML ops. It's just a bunch of different good practices and ways to kind of deploy this type of application in production, following certain specific um, we can call so. So just very much they provide different best practice and patterns to deploy this in production. You know. So LLM seems to be magical, but they hallucinate a lot. So how we can solve that problem? And the problem with hallucination, there is a lot of perspective that has been provided in the literature to understand why this model hallucinate. But for me, I think that one that I found kind of more makes sense is that from the perspective of knowledge compression, we are taking all of these terabytes of text written and we are feeding this data into those models. We are trying to those models learn semantic uh, relationships between all of these informations. But at the end, what's happened is that what we saw, we take the test and we transfer the data into a latent representation that we call embeddings. So this conversion from coming from a sparse representation to a dense representation, there is a loose information there. There is a loss of information in that step. So this is why these models sometimes hallucinate.
So, Henry, we have a quick question here from
Uh-huh.
Tapisya. Um,
Sure.
she has raised her hand, so I'll let her ask it.
Hey Henry, thanks Anne. Um, I actually wanted to ask in the previous slide, you had mentioned about if you could go to the previous slide. Yeah, it says in the front end, ChatGPT is no internet. I quickly tested ChatGPT is saying that the
Yeah,
internet is
up to day
required
I should up to date is relies on internet. Yeah, right now this is something that I forget to update. Yeah, but ChatGPT today can go to internet. Well, but when they release release it there in 2021, I think. So
Mhm.
they the model itself just pure relied on the data that was used to train. I don't know if you used to remember that we used to ask question about 2023 or 2022, and the model wasn't able to kind of figure it out how to. But today,
Mhm.
so yeah, this model actually they use things like as I mentioned, function calling and this stuff to go and get information from it.
From the internet. Okay. So, is there anything which is no internet conversational interface right now? Because most of them I think are internet dependent.
Well, I think that this is depend also the kind of implementation. This is the um, industry level implementation that we find today. Like talking specifically about Google and OpenAI, but there are some solutions that require 100% to be on promise, and you don't want to this kind of solution go to internet to grab any information. So you can run these models today locally in your own infrastructure. So in such a way, you don't require to go to internet uh, for anything, at least that you really require to grab any information from outside of the context that you have.
Okay. Okay, makes sense. Thank you, Henry. Thanks, Anne.
Hmm. Yeah, so that's mean that this model hallucinates, and I already explained why those models sometimes hallucinate. And so what about how we can deal with that? So how we can make the model to do exactly what I want? So well, we can improve our prompt engineering skills. We can do apply techniques such as style decomposition. We can do fine tuning to make the model more specialized. So what about if like another problem is that those models they don't know everything that you want to them to know. Well, this is when you start thinking about using RAG to provide the model with the information about your context. So that means that the model not will rely only in the general knowledge, but it's gonna also extract information from your databases or your documents. So it's hard to go from a prototype to a reliable production system. I think that is still happening. There is still a lot of challenges to uh, put this kind of solution in productions. But today we have LLM ops and a lot of kind of best practices that we can rely on to be able to deploy this into production. Into a um, certain of a level of quality. Um, what else? So they can only process and generate text. But this is not a problem anymore. So we have these multimodal models such as Gemini or I don't remember. I think that OpenAI also have the GPT-O that is multimodal. So this is not a problem anymore these days. Also we have some open source um, visual visual models such as Lava or that we can also use for this kind of application. So we have so these LLMs have opened the door to a wave of emerging architecture and design patterns and developing applications. And when this technology with this boom start um, in 2020 or 2019, we were focused only on understand how we can interact with this model to different prompting techniques, doing prompting engineering. But these days we start jumping into having autonomous agents, that are multiple LLMs collaborating each other, collaborating to solve more complex problems. So there are different ways to improve the performance of these models. Like track is just one way to do so, providing the model with information regarding to your context. You can also do fine tuning to make your model more specialized. And in terms of production, we also have a bunch of different techniques such as caching and what rails, where um, it's gonna ensure that the input and the output of your chat or your solution um, follow the roles that you define or safety constraints that you define. So how we can start developing application today? Well, I am out of time, but I'm gonna go pretty quickly. So first, we need to make sure if for the kind of application that we have for the use case, we really need to use LLMs. A bunch of different problems that we have out there, so it can be solved using traditional NLP approaches. So this is the first thing that uh, we can check, and so you guys can go and check it out. This paper, harnessing the power of LLMs in practice, and you can see this kind of workflow that tells you kind of framework that you can use to potentially identify the kind of tasks that you are trying to solve really required to have um, LLMs or not. The other question that you need to ask yourself is like, what kind of model do you need for your application? And here is when we start thinking about if we're gonna go for commercial LLMs or proprietary LLMs that we're gonna require to have connection to internet all the time because we just very much interacting with an API and sending the information and getting information back. But these days we have open source LLMs and solutions like Aulama that and NVIDIA have a lot of kind of inference engine that enable us to run these LLMs locally into our own infrastructure. So that means that or information never gonna go out. And the way that we can actually evaluate what is the best model for us is also could be in terms of the performance. So generally, the way that we can decide which model is more appropriate for our application is we can go to the leaderboards. Like one of the more well-known leaderboard is this one, Open LLM. I think that is. This one is another one. Well, there are different leaderboards. Like there is one in Hugging Face when you can see which are the best model for the different tasks. You can actually filter by task and identify which of those models are the best for. And another way you can just do your own evaluations, and there are different ways to evaluate this model. You can use point-wise evaluation techniques, which is taking the output of the model and um, just apply different quality checks and metrics that is gonna tell you about if like the quality of the output itself. Point-wise means you pass the prompt to the model, you get the output, and there are different ways to evaluate the quality of the output. But sometimes you want to compare two models each other to see which one is better. So this is what we call pairwise evaluation. So there are different techniques to do so. I highly recommend check it out the Vertex AI evaluation metrics. They provide tools for point-wise and pairwise model evaluations, and just with a few lines of code, you can actually have a benchmark of different models. So this can help you to figure out what is the best model for your application case. If, okay, so the other question that you need to do and you need to ask yourself also is that, so do I really need so do I how I can actually optimize my model and make my model more specialized for my context. Like you can find out that probably the models that you are using in your application is not giving you the kind of output that you expect. Specifically in those applications where involved to have a very specialized vocabulary. Like a biologic application or medical application, when you have these kind of terms that are very kind of specific for these applications. So in these kind of scenarios where there is a high probability that these kind of instructions are out of the context of the general knowledge of the model, is where you actually start thinking about the fine tuning. So especially because these kind of problems is not this kind of problem couldn't be solved by using RAG. RAG is for just provide the model with out of the information regarding to your content. But when we talk about fine tuning, is making your model more specialized and more kind of focusing into your context. So at the end, these models, LLMs, talking about LLMs and generative AI models in general, so um, they're fit into one category that is called in the literature like AI guide content generation, because they, in the way that generally they work, is that they follow these three principles to operate and to generate the output. First, when we pass the prompt to the models, what the model gonna try to do is just try to extract the intent information from the given instruction. Gonna try to figure it out. So what are you trying to mean? What you want the model actually do for you? And in the way that this model actually do so is just by using the information that you are providing in the context. So then when we So in the way that it's actually happening is that this information is transformed into embeddings. So that embeddings is passing to the foundation model, and then the foundation model is going to generate the output based on these identified intentions. That means that if we can provide the amount, see we can, so the likelihood of the probability to get the output closer to the kind of output that you expected is maximized based on the context information that you are providing. If, just try to provide as much of content that you are able to, so this cannot give you the model to the. But everything is about the content. When we talk about chats, so is people think that this model have memory, and this model, at the end, what is going on under the hood is that this model. So every time that we do a chat interaction, like we we send a prompt to the model and we get the output. We are just saving that information somewhere. This could be in a database or whatever. But every time that we prompt the model one more time, so we're gonna pass that information into the content. So that means that when we talk about chat application, we're actually made the model to be able to remember your name and all of that information that you. It's because we have provided all of that information into the context. The same happened with RAD application, but the RAD applications, rather than relies only in the information that we are just collecting during the chat, chatting with the model. So the application is, or the model itself is going to be able to extract information from external sources. And then the way that we do is that we're going to take a bunch of different documents or information that you want the model to be able to access to solve or address your questions. And we're going to transform that into embedding, so we can pass that save the information to an embeddings database. So then every time that we prompt the model, so the model is gonna try to find, well, the model no, it's gonna be a mechanism in your application. It's gonna be the retrieval part that we're gonna try to find which documents are somehow semantic close to that prompt that this can be potentially aligned with this prompt. And then we take those documents, we brought out those documents into the context, and we pass that into the prompt. You know, so this is exactly how RAGs work. Function calling is exactly the same. It's about context. So what I will do is that I'm gonna pass into the context the description of each function and what that function does. So then at the end, every time that I try to kind of come with a specific question that require one of those functions to be called, so the model is gonna try to figure it out that these functions kind of fit into the description. Then it's gonna give you the name of the description and and the parameters. So, but all of this need to be guided during the setup of the model. You need to say you're gonna be you're gonna be a chat, you're gonna be an assistant, and you will have access to these kind of tools. So please, every time that someone asks about something that can be, like use this tool to solve the question or whatever. And agents is the same thing. In agents, it's just a combination of having LLMs. Agent is kind of like combination of all of these kind of things that we have discussed so far. We have the LLM, which can transform or prone into a set of instructions that tell the model what actually the model needs. And the agents can actually access tools to grab information from the environment, you know, and then that information can be used and be passed into the context. So that means that the model can actually use that information to address problems. But agents in generally are systems based on LLMs that can interact with the environment. And the way that they actually do so is through the use of tools and things like that. So these days, people start using LLMs as a reasoning engines because the capacity of this model to understand text. This model are really good transforming text into structured data. That means that we can use that even for orchestrate analytical pipeline and do something stuff more sophisticated. People actually are kind of aligned with the aware of are actually aligned with the idea of that potentially LLMs can be incorporated into a kind of kind of LLM based operating system, because if LLMs can process multimodal data, but they can actually understand and make decisions using reasoning steps, so I can actually use that to operate a computer. So LLMs have been using for scientific discovering for different tasks. But let's talk about reasoning. People these days are talking about that these models can be used for as a reasoning engines. They are really smart. They can actually be used for to solve complex problems if you are able to instruct the model in such a way that you specify how the model can solve this kind of very complex. So, but let's get back to actually what if this is actually really means reasoning. You know, when we get back to reasoning, the definition of reasoning is the action of thinking about something in a logical and sensible way. You know, this kind of is aligned with the way how these LLMs work because again, so these models are autoregressive, so that means that they pretty much, the autoregressive nature of LLMs may lead us to believe that they are capable of this. Like if you recall when our grandma used to tell us that, think before to talk, you know, think your words before to actually say anything. So, and the autoregressive language, autoregressive nature of this kind of language, which tell us that every token is generated based on the previous steps and based on the previous token. It kind of, lead us to think that this model somehow can be talk about, like reasoning engines because they somehow kind of take in consideration the information that they have collected in the past or the set of facts that they have in the memory, so they can use that to address any question. So at the end, what we have is that we have the we are trying to come with this way to predict or solve a problem based on the probability of certain of steps that the model is going to be able to follow to be able to get into the point to they can solve. Okay, so there are publication about that. Um, but this is still being a controversial claim, This is still being um, a controversial claim because there are publications that they have done a lot of benchmark, and so far what they have come with is that um, so LLM is still far from achieve acceptance performance and complex planning reasoning tasks. However, there is it has been like a really interesting publication recently about how these models can be used for planning, and we're gonna probably share them at the end of the. But the other thing is that why people is thinking that this is kind of controversial is because there are some studies that shows that the reasonability of human is not necessarily um, correlate directly with the language. So that's mean that this somehow is gonna change if this model actually really reason in the same kind of such a way that human does, or they somehow come with this different way to kind of solve problems similar to what we do it by like through different reasoning steps. So today the only thing that we can certainly say about LLMs is that they are universal approximators for retrieval tasks. The capability of these models to be able to understand and reason and plan is pure based on the capacity of them to grab information from the environment, using techniques such as RAG, but also based on the autoregressive design of these models that can enable them to kind of reflect about the output and then take in consideration the previous tokens to generate the final response. So far what I see today is the multi-agent application of the future. So this implementation of adding the capacity of LLMs, multiple LLMs working each other and communicate to solve problems, have shown that they have maximized the so they have enabled LLMs to be used to solve more complex tasks, you know, and also not only that, like this, some of the good thing about agent is that they somehow reduce the hallucination because we can have these reflected patterns when we can have one LLM and two other LLM, and then they can work each other, and one can be the judge of the output of the other one. So that's mean that this collaboration between LLMs open the world to open the open the door to a bunch of different opportunities. But um, at the end, LLMs are really smart and they can transform non-structured data into structured data. They can access external sources and information using things like a function calling. They can rely on update information using techniques such as RAG, and they can communicate each other, and they can be integrated into this loop of interaction in a multi-agent system. And this is the kind of architecture that we have today that are being implemented to automate tasks such as software development or other kind of tasks. So anyway, but it's important to be aware that LLMs are not sort of true, and still a lot of challenges there. And there is a really good publication that is called it's titled 8 Things to Know About Large Language Model. So I highly recommend go and check it out. But yeah, this is all that I have prepared for today. So this is where we are today. If you want to know more about all of this in practice and you want to see code, so I have a GitHub repository that is. Um, you can go and visit my GitHub and you can find Gemini Workshop. And here in LLM apps and machine learning foundations, you can find things about like the embedding space, what is the meaning of feature space, what is the difference between traditional machine learning models and deep learning. So different example of racks, multimodal racks, and like how you can do a multimodal rack, how you can dark a rack, how you can do agent using Gemini API, how you can do function calling, multimodal reasoning engine, and all of this kind of stuff. So you can go there and check it out the code, and feel free to reach out if you have any questions. So you have my information, and I will be happy to chat about these topics, which are part of my daily research. Thank you.
It was a great overview and great talk, Henry. I think we got all the questions answered in the chat. Um, People are asking for slides as well as the GitHub link, if you can share those.
Yeah, I will probably just put that into a file and share it to you so you can email to the attendants.
It's good.
But I think there is one question in the chat in the so you guys can unmute.
Yeah, I
And
think,
ask.
Arjav has his hand raised.
Right. Yeah, actually, I just had a quick question. Am I audible? Okay. Yeah, so I had a quick question regarding like the topics towards the end of the slides regarding reasoning. So I did hear that you mentioned that it's sort of like a controversial area about whether like LLMs can reason yet or not. Um, but I just wanted to like ask you like, about your thoughts on the newest like GPT model of which is like O1, which like I've like tried out the model as well, and like there's that popular question of like how many R's are in the letter strawberry, where like the older models weren't able to answer that because they just read the word strawberry as one token. But, like the newer ones are able to answer that question now, and actually like it it thinks quote unquote and is able to answer that question correctly. So I just want to like ask you your thoughts on what sort of improvements, I guess, or what is it that's being done differently for like these newer models to be able to reason, I guess, or like be able to like answer these questions which they weren't able to like evaluate properly before.
Yeah, this is a really good question. So there is a lot of so there are two aspects of how this model has been trained. So I think that the difference between how these models are trained in comparison with the um, others is that according what the report that they release is that they train those models to follow instructions and reasoning steps. What they actually mean is that so there are techniques such as React. React is that I mean I don't know if are you able to see here is that the traditional way that you prompt the LLM is you just go out, you just go and then write down the prompt. The standalone way that you interact with the model is that you just write down the question and you expect the output from the model. In the standard way as you see here. You ask a question and you get the output. So, but you can also, as I mentioned before, there are different ways where you can actually make the model to generate smarter outputs by providing with intermediate steps, such as this is the idea behind of frameworks such as React, synergic reasoning. There's one paper published by Google. I don't remember exactly when, but anyway, so in the way that I actually have is in the context or in the context of the prompt, you're not gonna provide the LLM only with the questions, but you're gonna also provide with these reasoning steps that you define in this way: thought, act, and observation. So then you say, for this question, for instance, aside from the Apple remote, what other device can control the program Apple remote? Blah blah blah. So then you're gonna provide like thought one. I need to search Apple remote and find the program that it was originally designed to interact with. Two, Apple remote was originally designed to control. So pretty much that is a completely different shift between in the how you prompt the LLM. Instead to just do a standalone prompt, you're gonna provide with this thought act observation, thought act observation. So this is what they have found that enable LLMs to start kind of like think about it and generate output that actually kind of makes sense because they generate these kind of steps or this set of reasoning steps that lead us to think that these models are doing some kind of reason. So the difference between these
Sorry, no,
models
I
that
just wanted to. Sorry. I'm so. I didn't mean to like interrupt. Sorry. I just had like a quick question regarding this. So, like in this process, like it is. I guess this is like a little more dependent on the user to be providing that sort of input as a prompt, right? Like, but if I'm just giving it like a vague statement, even now in like a newer model, like are you saying like the model is able to sort of give itself those like independent prompts which are like broken down, and that's how it's able to reason?
exactly because
Okay.
the model that OpenAI just released that they say that they kind of like tune specifically for reasoning tasks is what they did is they fine tune the model to follow this kind of reasoning path. You know, instead
Right.
to instead to fine tuning the model to just this is the question and this is the output, you're gonna fine tune the model in such a way that this is the question and this is the reasoning step that you're gonna follow to get into the answer. But on top of that, there is a lot of work done, a lot of work that has been done into the inference part. So,
Mhm.
because instead you manually need to kind of come with this prompt, when you pass the prompt to the LLMs internally, what actually is going on, it tries to infer based on your question how decompose that question in such a way that fit into this kind of reasoning step mindset. You know, so that's mean
Right.
that so this is what actually made this problem different. Indeed, there is a really let me see if I can actually grab it, but uh, yeah, but there is a lot of stuff also that happened in the inference part. Like I don't know if I can. Uh, Yeah, but this is the reason why, this is why probably the model is not really good addressing those questions, kind of generate the next token or identify. But if you ask probably a question where the model need to think about it or generate a set of steps to be able to come with a solution, he's probably gonna do a good job for that.
Right. That makes sense. Thank you so much. That was a pretty clear explanation. Appreciate it.
Yeah, and this is exactly what I wanted to show you. Is this? You see this thing here? Most LLMs they are pre-trained, and then they fine tuning or like to do a specific task. But what they
Right.
do here is that they pre-train and then fine tune to follow like reasoning steps. But then they do a lot of the stuff here in the inference part because they don't expect that you to need to provide with all of this set of kind of talks, acts, observation, and so on. But
Right.
what is going to happen internally is that they have some components that try to cope with this prompt in such a way that the models can be, you know.
Right. So that makes a lot of sense. Thank you so much. I really appreciate it. And thank you for the session as well.
Mhm. Any other question?
So I see one from Saba in the chat. Uh, he, I think, is looking to take a peek of the slide that preceded the one titled Augmented Language Models.
Which one? Okay.
The one before Augmented Models.
Which one?
Yeah, I think he's probably talking about that one. Is this the one you're looking for?
Yeah, so right now today what we have is that this is a standalone way that we prompt to the LLMs. So for reasoning tags or this kind of complex prompts, so well we have these techniques which is what I just explained, like React. And for those that they require external knowledge, so we rely on RAG system or tools to grab the information from different sources and then grab it and put it into the context. Or if we require any, so for the require computation in that, so recently papers have found that, for instance, for math problems, it's better for the models. The model is got better if instead to try to predict the output just per based on text, he just takes some of the try to extract some of the variables and on the process from the prompt and then pass into the Python function that can be executed into the backend and then do the computation and generate the outputs. So this is Gemini, for instance. Today have something that um, they can execute code. So this is code execution. This is very useful feature for specifically for math question or this kind of things. So
I
what is the
think
question?
Saba was disconnected. If you can open that slide again. What was your question about it, Saba?
Thank you. No more specific question. I was just screenshotting and I didn't get this one. But yeah, thank you.
I think
This is great.
we should be able to share the slides with you. So yeah, you shouldn't need to take these screenshots. Hopefully, we'll get them out soon by.
Yeah, but the only thing that you guys need to understand is that all the LLM design patterns are around different ways to use context. We have chat. It's just putting the chat history in memory in the context. You just use RAG. You just bring information from external sources that has been stored into a vector database and grab those related documents that are kind of semantically somehow close to the prompt and bring that into the context. Agents, reasoning, all of these kind of studies rely on different prompting techniques, and this is so far how it actually works. Okay, so there is any other question?
Great. Looks like there are no other questions in the chat. There's a hand raised by Ina.
Hi, yeah. Hello, Henry. Thank you so much for
Hello.
the talk.
Mhm.
I wanted to ask you to talk a little bit more about the benchmarks as well from the previous slide. How do you select those, and what would be a good one, right? And then the
Okay.
second question, sort of, and I know you touched upon it a little bit, would be the testing. So far, it seems that a lot of testing of your model is just like prompting and seeing a result, right? Are there any like automated ways to test the performance of your application or any recommendations to that? Thank you.
Yes, like oh, regarding the first question, so there is one particular the general in the way that you actually pick the best model that fit into your application is that you first check into the leaderboard, which are the model that has shown better performance in the benchmark. So the leaderboards that people is using these days is that what is called LS. It's called you can just find chatbot arena leaderboard, and you can actually come here and and filter out the benchmark based on which one are better for math, which model are better for math, which better for coding, which are better for instruction following, which models are better for longer queries, English, different languages. So this is one of the way that this is generally the kind of filter that you first start doing. Then you start jumping into like if it's a proprietary model or it's a local one, and based on that you can start thinking about how you can deploy that into your integrate that and plug and play that LLM into your application. Now regarding the other question that you asked was about what is the best way to evaluate the performance of these models, right? You're talking about the
Yeah,
model
sure.
itself or the applications?
No. Yeah, the first question was about benchmarks, so model evaluation sort of, and the second one was about like testing the application powered by AI or LLM model.
Okay, yeah, in those kind of scenarios, there are different tools, So again, what I mentioned is that to evaluate these models, so you need to be aware what kind of component your application has because you can use one LLM for something and another LLM for another step, and you can. What I mean is that you can have multiple LLM doing different things. So these kind of complex scenarios require that you need to evaluate each those model independently, and then so you are able to kind of estimate or identify which of those components into your application there is a need for improvement. So there are different ways to evaluate these models. Again, so there are different metrics. So there are metrics based on point wise. Point wise is mean you get the model, pass the prompt, and get the output, and you apply those point wise metrics in the output to generate different. There is a framework that is called RAGAS. You know, so this framework provide a bunch of different metrics such as faithfulness, context precision, context recall, context utilization, context noise sensitivity. So all of these, you just pass the question, the answer, and the context, and it's able to generate different numerical metrics that you can use to estimate the performance of these kind of models closely. Another thing is that if you are using this model um, downstream tasks such as classification of text or summarization or these kind of things. You can create a data set or where you have the input and the outputs, and you can try to come with your own custom metrics that are aligned with the kind of performance uh, measurement that you want to have in your application. And based on that, so you can do your own evaluation, implement your own evaluation pilot. But so far, this is kind of the way that you have to to do so. Like this is why point wise, but pairwise is comparing multiple models to do on a specific task. I don't know if
For
this addresses your question.
I see. Thank you so much. Raga
Mhm.
seems really cool.
Yeah,
and
this
for
was really good.
point-wise evaluations, there's another thing that I've seen being used. They call it LLM Judge, and what it does is you pretty much describe the criteria you want to rate the response of your LLM app against, because your use case might have very specific requirements, like you want to judge it on the basis of say you are requesting it to come up with a list of tasks, then how specific are those tasks, or do they align with what the user had asked for, things like those. You just use another LLM to judge the response of your LLM app, and it takes some manual effort to tune it right, but it we have been using it at some use cases at my workplace. And yeah, for pairwise as well, like another thing that has helped is using an LLM agnostic interface such as Llama Index or LangChain to write your logic for orchestrating these LLM calls, so that you can quickly swap the LLM that's powering the app and test out both.
Yeah.
Cool. Thank you so much.
Mm-hmm. More questions? Okay. Well, thank you so much for attending the workshop. So it's a really interesting topic that um, I highly recommend and encourage to keep researching about that. Like there is a lot of stuff going on in terms of reasoning these days. So you guys should get back and try to explore how these models are being used for that.
Yep. And yeah, thanks so much everyone for attending. We would love to get your feedback on this event. If you can visit this website, tiny.cc/gdg feedback. It's just a small, quick form, but it helps us figure out what events you would like to see next in the future. So please do take the time to fill it out. It helps the community a lot. Um, and yeah, as always, thank you so much for joining. Thank you so much, Henry, for carrying out this talk. Really great to see you out here after, I think, quite a bit. Last event we did here was, I believe, last year. So
Yeah.
it's been great to have you again here. And hopefully we can do more events. Maybe people want to dig deeper into these LLM apps and see some examples of those and do a workshop. That'd be really cool. Um, yeah, great talk.
Okay. Thank you. Yeah, I think that there's a problem with the link of the feedback.
Yeah,
Let
there's some.
me check that link. Maybe it's down. Okay, there's not a dash in the link. My bad. Let me type that again. Okay, this one should work. Yep.
Okay. Thank you, guys. Have a wonderful weekend.
Thank you so
Bye.
much.
Thank you. Bye.
See you the next week.
Thank you. Thank you very much, Henry.
Thank you
Thank
so
you.
much, Andre. Thanks, Anne. Bye.
Thank you.